So all that being said, and thankfully not recorded. Unfortunately for y'all, you had to live through it live, but those are the benefits of being late to class, I guess. We want to start talking about trigonometric identity. Here's what we mean when we talk about identity. An identity is an equation that's always true. I just said always, and this is math class. You should never say always in math class. It never works. So let's clarify. An identity is an equation that's true for all the valid values of the variable. So an identity, we shorthand this to say an identity is an equation that's always true. Secretly, we've used these before in algebra. So if we had an expression that said 2 times x plus 5, that's equal to 2x plus 10. Adding 5, multiplying the result by 2 is the same as multiplying by 2 and adding 10. This is true for all x. That's why when we see one, we can just replace it with the other. They're always going to be the same. However, if I write the equation 2x plus 10 equals 18, that equation is only true when x is equal to 4. But 2 plus 4 is equal. Yeah, I actually got it right. 2x plus 10 equals 18 is only true when x equals 4. This is a conditional equation. A conditional equation is true under certain conditions. This equation is true under the condition that x is equal to 4. If x is equal to 4, this equation is true. If x is anything but 4, the equation is not true. An equation that says x plus 1 equals x plus 2, this equation is never true. No number is equal in value to the next number. This kind of equation is called a contradiction. An equation that's never true is called a contradiction. No, I just wrote it's never true. So a contradiction is an equation that's never true. So we've got identity, always true. A conditional equation, sometimes true. A contradiction, never true. Identity, conditional, contradiction. I just realized I have to be read for the contradiction, but There's the first pen I grabbed at the top of the paper, so got to make sure that some exclusions apply, because we can have an identity that's not true for some values of the variable because the expression isn't defined. So, for example, x over x squared is the same as 1 over x, as long as x is not 0. If x equals 0, both expressions are undefined. We're going to count this as identity enough. There's only very specific cases where the expression equation is not true. It's not true for x equals 0 because both expressions are undefined at x equals 0. So it doesn't really make sense to try to put an equal sign for things that are undefined. We don't say undefined equals undefined. But it's true enough. This comes up a little bit in rational equations, the rational expressions for the same thing. Sometimes we simplify things and we write things that are equations that aren't always true. So for example, we will usually write x squared over x. We'll usually simplify this to x. But these expressions are not always equal. When x is equal to 0, the left side is undefined and the right side is 0. That can't be. But they're equal enough. So really, it's kind of a meh. Equal enough. If we want to well actually the whole situation, we can put a comma and say x can't equal x not 0. So if you want to be pedantic, you'd be like, oh, well, actually, x squared over x is equal to x, as long as x is not 0. At which point it's like, oh, dude, you know what I meant. These kinds of things are especially dangerous in a math class because math teachers are randomly pedantic. There's no math teacher that's all pedantic all the time, but they might be extremely pedantic about certain things and like just ignore others. What's worse is that they don't recognize this. So I try to recognize the things that I'm pedantic about so I can call myself on it when it comes up. Any questions? Here are some trig identities you need to recognize on site. These are going to be the tools that we have in our toolbox for simplifying expressions involving trig functions or for proving trig identities because we want to have an algebra workout. Number one, or first category, tangent theta is sine theta over cosine theta cotangent theta is cosine theta over sine theta. We'll refer to these two as ratio identities. Another important category. Secant theta is 1 over cosine theta. And that means that cosine theta is 1 over secant theta. Sine theta, or sorry, cosecant theta is 1 over sine theta. So sine theta is 1 over cosecant theta. Why didn't cosecant go with cosine? There are reasons. Not important. It's important to notice that and remember they don't go together. Secant and cosine are related. Sine and cosecant are related. We'll refer to these as reciprocal identity. Show us all the reciprocals. It's important to remember these because one of our strategies that we're going to use in simplifying trig identities or simplifying trig expressions and proving trig identities, one of the strategies that we like to use is write things in terms of sines and cosines. So one of the strategies that we're going to have so these are important when we are writing things in terms of sine and cosine. That's one of the strategies that we might employ. These are all identities that we don't just recognize on sight. We have to have instant recall. We have to think of these as possibilities. Here's one of the things that makes trig identity, simplifying trig expressions difficult. We might have to make choices about what to do. We often think that we like to have choices, but we really just want one path towards the answer. One path towards the answer, we can preload all the things that we'll need. This is going to require a random access. We're going to have all these things just waiting there for us so that when we see something in our trig identity, it will make us think of the ones that all of our tools. Any questions? Is everybody okay? Everybody looks so very sad today, which means it's working perfectly. Was I using theta or x? That was theta. No. The next category is Pythagorean identities. And it all comes from this one. Cosine squared theta plus sine squared theta equals 1. Each of these Pythagorean identities is going to have two variants. We could write 1 minus cosine squared is sine squared. Or 1 minus sine squared is cosine squared. It's helpful if you have all of them loaded up and ready to go. It's necessary to know which functions are related in the Pythagorean identity. It's also important to recognize that cosine squared plus sine squared, we can turn that into another Pythagorean identity. So if we take this identity and we just divide everything by cosine squared, we get cosine divided by cosine is 1. Sine squared divided by cosine squared is tangent. And 1 divided by cosine squared is secant squared. So there's another Pythagorean identity. You want to recognize that secant and tangent are related in a Pythagorean identity. We can solve for the tangent squared. If I subtract 1 from both sides, I get tangent squared is secant squared minus 1. Or I can solve for 1 by subtracting tangent squared. Bringing us 6 Pythagorean identities. Moving forward, these would be the 6 to know, but there is another. We took this cosine squared plus sine squared. We started off, we divided by cosine. So we should have seen this come in at the beginning. We're now going to divide by sine squared. So cosine squared divided by sine squared is cotangent squared. Sine squared divided by sine squared is 1. And 1 divided by sine squared is cosecant squared. So what we need to remember is that cotangent and cosecant are related in a Pythagorean identity. Then we can do the same thing. We can solve for cotangent. Cotangent will be cosecant squared minus 1, or cotangent squared. So if we do cosecant squared minus 1, that will be cotangent theta, cotangent squared theta. And that means cosecant minus cotangent, cosecant squared minus cotangent squared is equal to 1. These are our 9 Pythagorean identities. Nine Pythagorean identities. We're gifted to the students of trigonometry who above all desired passing grades. That was the original setup in Lord of the Rings in my hall. What if instead I wrote some down. You can't just make these things up on the spot. Well, you can, but it never works out well when I try. All right. So here's how we play the trigonometric identity game. We're going to have expressions on either side of the equation. We want to show that the equation is always true. Our goal is to prove that a trigonometric equation is an identity. So let's suppose we have sine theta times cosine theta times tangent theta is equal to 1 minus cosine squared theta. This raises the obvious question, why would we care? To which the response is pretty much, quiet you, this is what we're doing today. And you're like, all right, lateral raise it is. Now do lateral raises and walking lunges at the same time. You're like, all right. Why are you having me do this? Because it'll be funny on YouTube. And you turn around and they have a camera. All right, so the idea is I'm going to start replacing stuff on one side of the equation. I'm going to rewrite one side of the equation to make it look like the other side of the equation. So our strategy is to use identities to rewrite one side of the equation into the other side of the equation, into the other side. Big idea here is we're just going to use identities to make one side look like the other. One thing that we should avoid doing is treating this like an equation that we're trying to solve and do things to both sides. Don't do stuff to both sides of the equation. That's what we do when we're trying to solve an equation. And we're not doing that here. We're not trying to solve an equation. So we're not going to do stuff to both sides. I want to make the left side look like the right side. So I'm going to operate on the left until it looks like the right. So notice on the left, we've got sine, cosine, sine theta, cosine theta, tangent theta. So I'm going to employ our number one strategy. Write everything in terms of sines and cosines. So I'm going to replace tangent theta with sine over cosine. Tangent is sine theta over cosine theta. The reason that we want to do this is that this makes something happen algebraically. That's really what this is about. This trigonometric identity game is all about making something happen algebraically. What happens here is that the cosines cancel out. And so this looks like sine theta times sine theta. sine theta times sine theta, we write as sine squared theta. And sine squared theta is equal to 1 minus cosine squared theta. One progression from one side to the other with identities. That's 6 degrees of Kevin Bacon. And then the last step is, and John Lithgow was in Footloose with Kevin Bacon. Any questions? Here's another one. Cotangent x over cosecant x is equal to cosine x. This one at least makes sense. It makes sense that I would want to write cosine x instead of writing cotangent x over cosecant x. Why say this whole mouthful of cotangent x divided by cosecant x when I could just say cosine x? So I'm going to start on the side where I can replace everything with sines and cosines. So I'm going to say cotangent x over cosecant x is equal to, cotangent is cosine x over sine x. And cosecant x is 1 over sine x. At this point, we should see that the denominator in the top is a sine x, and the denominator in the bottom is a sine x. We have a common factor of 1 over sine x that we can cancel out. We're usually not trained to see it that way. So I'm going to write the top cosine x over sine x divided by 1 over sine x. That's what that fraction means. I just take that vertical division and write it as horizontal division. Now I want to divide fractions, and that means multiplying by the reciprocal. So this is going to be cosine x over sine x times 1 over sine x over 1. And now we can see that the signs are going to cancel and leave behind a cosine x, just like we planned. Or just like we were hoping for. So here are two examples of the strategy of replace everything with sines and cosines, right? Everything in terms of sines and cosines, see if that makes something happen. The point is we're trying to make something happen. Really, there's just one instruction, make something happen. Questions? Comments? Snide remarks? In case you are wondering if it's death by examples today, it is in fact death by example. So the idea is to make something happen. In this case, we have an operation that we can perform. If your identity, if one side of your identity involves an operation that you can perform, then perform that operation. There's something that can happen right here. There's some algebra that we can do on the left. Our brief is to make something happen. Let's multiply that stuff out. 1 times 1 is 1. 1 times cosecant is plus cosecant. Minus sine times 1 is minus sine. Sine times cosecant, negative sine times cosecant is negative sine x times cosecant x. The brief is to make something happen. Here, something just happened. There's some algebra for us to do. So we did that algebra. Now we're going to look at what we got. We got cosecant minus sine. Let's see, we got this sine and cosecant. Is there anything going on here? And we notice that sine and cosecant are being multiplied together. And we remember that sine and cosecant are related in our reciprocal identity. So cosecant is the same as 1 over sine. Note that I'm not just changing everything yet. And I'm going to grab my reciprocal identity. Cosecant is 1 over sine. Now I can multiply sine x times 1 over sine x. All that's equal to 1. So now I'm looking at 1 plus cosecant minus sine minus 1. So the signs cancel out. Now I notice that the sine, now that I've canceled out the sine and the cosecant, made that equal to 1, or the sines, and made that equal to 1, I have a 1 and a minus 1. So now those cancel out. That's always awesome when you're doing this and some terms cancel out. Like, oh, heck yes, I will take that. So we got cosecant x minus sine x. Now I go, oh, well, shit. That first thing, do some algebra. We did that. And a bunch of stuff happened. Sine times cosecant became 1, and that canceled out the 1 at the front. So we dropped out 2 of the terms on FOIL. Now we're at this point, we have to make something happen again. So we go back to the old strategy. Cosecant is 1 over sine. So write everything in terms of sines and cosines and see if that gives you something to do. And here it does give us something to do. Now I've got a fraction minus sine x. I have an algebraic thing I can do. That algebra thing to do is to add fractions. If I add these fractions together, maybe that will give us something. So I'm going to read that sine x as sine x over 1 and get a common denominator. I've got 1 over sine x minus sine x over 1. And I'm going to get a common denominator. Now I've got 1 over sine x minus sine squared over sine x. And now we can do the algebra that we wanted to do and write this as 1 minus sine squared over sine x. Now that we've added the fractions, we said we need to make something happen. So I traded my cosecant for a 1 over sine. That gave me fractions, so I added them. I made an algebra happen. Now I'm looking at this one fraction, 1 minus sine squared over sine x. So we got to see this 1 minus sine squared. That should make us think cosine. We should be primed to be looking for cosines because the other side has cosines and cotangents in it. So we're going to look at this 1 minus sine squared, and we're going to say that's cosine. We can use Pythagorean identity here. So our algebraic efforts have paid off. Another identity showed up. Now, if I break apart the cosine squared just means I have 2 factors of cosine. So I can write cosine squared as cosine x I can do some algebra on that, and I'll just make like that as cosine x times another cosine x. That's what cosine squared means. And this is all being divided by sine x, which means I can just divide one of them by sine x. And that gives us cosine x times cotangent x. Which was the whole point in the first place. That's what we were trying to write. So when you're trying to prove trig identities, generally you're going to pick one side, make some algebra happen. If there's some multiplication that we could do, like a FOIL, like in this problem, then FOIL. If there's fractions that we can add, then add those fractions. If there aren't any fractions, try writing everything in terms of sines and cosines. See if there's some fractions that show up then. And then just start looking for your identities to show up. Any questions? Yes. This one here? Yeah, so here I've got 1 over sine. And so the denominator is sine. And in this fraction, the denominator is 1. So I multiply to get a common denominator. Imagine if I wanted to add the fractions. 1/3 minus 5. Our strategy would be to get a common denominator, 3/3. Because we think of the 5 as being 5/1. So this becomes 1/3 minus 15/3. And now that they have the same denominator, we can add them. So in this case, the denominator was sine x in the first fraction and 1 in the second fraction. So my common denominator was sine x. So I multiply by sine x over sine x to get a common denominator. Is everybody okay? I always try to look for the basic instruction, the fundamental instruction. What's down there at the bottom? And here, it's about making something happen. Make some algebra happen, and then just do that algebra. How's everybody okay? Let's look at my next example, and I'm like, oh no. You're already all mad at me because of all this stupid algebra. If I do that one, there will be open revolt. The likes of which we have not seen since the early days of my teaching trigonometry back in the 90s. And I gave a final exam that I didn't really test for time. And then like halfway through, I realized like, oh, I don't think anybody's gonna be able to finish this. And I looked up and there was like a whole room full of angry students. I'm like, oh, you know what? This final exam is over. And they're like, oh, what's gonna happen to our grades? I'm like, oh, don't worry. I have to pay you for putting this awful final in front of you. Really what happened is you write a final, you do like one of everything. New teachers always do this. New teachers always hand out a final, and it's like one of everything, even the shit that don't matter. It's like, oh, yo, calm down, put less, make some choices. And I just handed out the one of everything final, and it was, that was funny when I realized it. But then I looked up and I thought, oh, everybody's all mad at me. Some students hadn't noticed how bad it was yet. Right? So the students that were just kind of like, so haven't noticed, but other ones had noticed just how bad it was because they saw what was up, they were up against, saw how much calculations, they looked at how much time it was. It's like, all right, I'm gonna have to murder my professor. Anyway. All right, that's gonna do it for today. That's gonna do it for this week. I'll see y'all on Tuesday. Everybody have a good day or weekend, and thanks for playing.